This is the 23rd video in our series on topology, and today we're going to talk about homotopies and homotopic maps. So let's jump right into a definition. So given topological spaces x and y, and then two continuous functions f and g which go from x to y, we say that f and g are homotopic, and we write, well, this symbol right here. It's important to realize that there's a single straight line, so there's the squiggly line and a single straight line. So that's different than the symbol for homeomorphism. Okay, so anyway, we say these things are homotopic if there exists a continuous function that we'll call capital F, and it goes from x cross the unit interval to y, and it satisfies the following conditions. If we evaluate this at any x and at 0, we get f of x. So if we think about that as part of capital F, we see that part of capital F is just our curve f of x. And then if we evaluate this at x and 1, we get g of x. So in other words, that's another part of our curve. And so here's a little SketchUp of what's going on here. So let's say these are our topological spaces x and y. And then down here, we've got our f of x. Up here, we have our g of x. And notice that our capital F kind of interpolates between f of x and g of x. Okay, so let's jump into our first result, and that says that any two continuous functions f from R to R are homotopic. But of course, we need two continuous functions here. So let's say they are f and g. And this is like almost immediate, the proof, and that is we consider the following map. So notice that it's got to go from R cross the unit interval into R, and it's going to be defined by the following equation. So f of x comma t is going to be equal to 1 minus t times f of x plus t times g of x. So that like continuously interpolates between these two curves. And observe it has the right conditions. So if we do f of x 0, well, that's going to zero out the g part, and we're simply going to get f of x. And then if we do f of x comma 1, that's going to zero out the f part, and we're going to get g of x. Okay, nice. And now we could look at a pretty straightforward example of this like this. Let's say perhaps we have, well, let's say we're doing an example here. Let's say we have f of x is the 0 function, and let's say we have g of x is the parabola x times x minus 1. And let's just say that we're taking x only on the unit interval, just to keep it simple. So notice that what we've got going on here is the following. So since we're only graphing over the unit interval, we only need to look at this, which is our copy of what f is doing, and then this, which is our copy of what g is doing. Okay, so there's our curve, f of x and g of x. And then, well, using this formula exactly, we can define f of x comma t to be equal to t times x minus 1. And so, of course, that's just going to build us little parabolas all the way interpolating between our f of x and our g of x. That should have been an f down there. Okay, nice. So in fact, the real numbers are not super special because of this. There are lots of topological spaces that have this property. And so let's write a general definition for which all topological spaces with that property will have this fact. Okay, so the definition we want to look at is we say x, which is a subset of Rn, is convex if given any x and y in X, the line segment from X to Y is a subset of X. And so in other words, for all t between 0 and 1, we have 1 minus t times X plus t times Y is an element of X. That just parameterizes the line segment. So let's do some examples. So let's observe that Rn is going to be convex for any n. And then also, like any open ball, inside of Rn is also going to be convex. I guess we could draw some pictures as well, like this thing like this, which is maybe like an ellipse, or maybe this blob type shape is most definitely convex. And then maybe this hexagonal shape is also kind of obviously convex. Now, what about some non-examples? Well, I think a kind of obvious non-example would be something like this. It's kind of a bean shape. So we see that that is not convex, because if we choose, for instance, this point right here, we'll call it X. This point right here, we'll call it Y. The line segment between X and Y goes outside of the set. Another example would be simply embed a curve into R2. So here we've got a curve inside of R2, and we pick maybe perhaps this point right here, X on the curve, this point right here, Y on the curve, and we'll see that the line segment between them is pretty clearly not totally contained inside of the curve. Okay, so now that we've got this, I'd like to maybe write a bit of a generalization of the previous result. And that is the following. Y is a convex subset of Rn, and f and g are continuous functions from x to y, where x is any topological space, then f is homotopy equivalent to g. In other words, f is homotopic with g. And here, what's the proof? Well, I'm not going to go through all the details because it's essentially the same thing as we had before. In other words, we'll use our function f of x comma t to be equal to 1 minus t times f of x plus t times g of x. Now, of course, we know that the codomain here, which is a subset of Rn, needs to have some sort of addition and scalar multiplication for this kind of formula to make sense in the first place. So we really are leaning on the fact that we are within Rn. Okay, so now let's move on. Okay, so now we're going to show that being homotopic is an equivalence relation. So it's going to be an equivalence relation on the set of functions from x to y. And so we first need to check that it is reflexive. So let's show that f is homotopic to itself, but that's like pretty quick because we can just define our f of xt to be f of x for all t on the unit interval. So it's not really a constant function, but it's like a constant curve, if you will. Okay, so now we need to show that it's symmetric. In other words, we want to suppose that f is homotopy equivalent to g, and then we'll show that g is homotopic to f. Okay, so let's see. This implies that there exists an f from x cross 0, 1 to y such that we have f of, let's see, x comma 0 is equal to little f of x, and f of x comma 1 is equal to little g of x. And now what we'll do is essentially we'll run this in reverse. In other words, we'll run the time in reverse. So instead of starting at 0 and going to 1, we're like starting at 1 and going into 0. But we can do that via like a little transformation. So let's do that. So let's define our g, which again needs to go from x cross 0, 1 into y. And we're going to define it by g of x comma t is equal to f of x comma 1 minus t. But this is going to essentially do it. And we'll see that via the following observation. So g of x comma 0 is the same thing as f of x comma 1, which is little g of x by our construction of our original map. And then also g of x comma 1 is the same thing as f of x comma 0, which is f of x. But all of this together tells us that g is homotopy equivalent to f. So that proves our symmetry. Okay, so now we want to prove transitivity. In other words, we will suppose that f is homotopy equivalent to g and g is homotopy equivalent to h, and let's say that is via functions f and g respectively. And now what we'll do is the following. So let's define h which goes from x cross 0, 1 as needed into y by the following formula. So h of x comma t will be equal to, well, so this is going to be a piecewise function. It's going to be f of x comma 2t if t is on the interval from 0 to half. And it's going to be equal to g of x comma 2t minus 1 if t is on the interval from 1/2 to 1. So in other words, we're like pasting these two things together and then maybe doubling the speed of time here. Now let's observe that this satisfies the right condition in order to be a homotopy between f and h. So if we do h of x comma 0, that's going to be f of x comma 0, which is little f of x. And so that's just by our construction. And now notice that h of x comma half is equal to f of x comma 1, and it's equal to g of x comma 0, again by construction. But that might seem problematic, like maybe this isn't well defined, but we're actually okay here because those are both equal to g, since we're saying capital F and capital G do these two equivalences. And now we'll check h of x comma 1, but that turns into g of x comma 1, which is h of x. But that means that h does the job that it needs to do to show that f is homotopic to h. Now let's see if this type of equivalence goes through compositions. Now let's look at this result involving composition of functions. So let's suppose that f and g are homotopic and they go from x to y. And h and k are homotopic and they go from y to z. Then h composed with f and k composed with g go from x to z just by composition of functions, and they're in fact homotopic. Okay, so let's see how this goes. So let's suppose that f is homotopic to g via f, and h is homotopic to k via, maybe we'll call this one g. So that just means they satisfy this setup over here. And now what we'll do is define the following function h. And so this function h needs to go from x cross the interval 0, 1 into, let's see, z. And well, let's maybe just point out where these f and g's go. So f goes from x cross 0, 1 into y, and then g goes from y cross 0, 1 into z, just based off the domains and codomains of our starting functions. Okay, so now let's see how this h has got to be defined for the whole thing to work out. So it's going to go like this. So h of x comma t is going to be equal to, well, it's kind of like the composition of f and g. So it's going to be g of f of x comma t. So look at what's going on here. F of x comma t is an element of y. So that means we're sticking an element of y here, and then applying this t, which means we get a z out in the end. Okay, so now let's make sure that this checks out. So here we've got h comma of x comma 0 is going to be g of f of x comma 0 comma 0. But that's going to be g of, and now f of x comma 0 is what? Well, it's our function f of x. Good. And then we've got a 0 here. But now what does g do? Well, g takes whatever we have here and it plugs it into h when we're at 0. So this is going to be h of f of x. Or, in other words, it's going to be h composed with f of x. Okay, good. And now let's look at h of x comma 1, but that's going to be g of f of x comma 1, but that's going to be g of x comma 1, but now that's going to be k of g of x. But then that is k composed with g of x. But now observe that this function starts at h composed with f, and ends at k composed with g, just as we needed it to. Okay, so now we're going to introduce another definition and work with that a little bit. All right, so our new definition is the notion of two topological spaces being homotopy equivalent. So x and y are said to be homotopy equivalent if there are two continuous functions, f from x to y and g from y to x, so that if you compose f composed with g, notice that goes from x to x, that's homotopy equivalent or homotopic to the identity function on x. And then f composed with g is homotopy equivalent to the identity function on y. Next up, we'll say that x is contractible if it's homotopy equivalent to a single point topological space. Now I've written that point as A, but it could be anything. It could be embedded in another topological space or kind of abstractly on its own. Now here's a bit of a homework exercise, which is pretty straightforward, and that is if x and y are homeomorphic, then x is homotopy equivalent to y. The converse is not true, and we'll see that the converse is not true with the following result. So for all n bigger than or equal to 1, Rn is contractible. In fact, you could have n bigger than or equal to 0 here because R0 is just a single point anyway. But that one you kind of get for free. Okay, so now let's define a function f from Rn to a single point by, well, how does it have to be defined? Well, f of x has to be equal to a. And that's because, well, there's no other choice there. Now, this is pretty clearly a continuous function because the only open sets over here are nothing and everything. And if you take their pre-image, you get, well, nothing or everything over here, which is also open. Okay, good. And then let's also define g from the single point to Rn by g of a equals, well, we're going to set it equal to 0, but it really could be any point inside of Rn. Okay, nice. And now let's note the following. So if we do our composition like this, let's see, g composed with f, notice that this is a function from Rn to Rn. Okay, but then we know that all continuous functions from Rn to Rn are homotopic. Well, we proved it for R, but the same proof works for Rn. In fact, because Rn is, let's see, convex, and we proved it for convex. So what that means is that this g composed with f is homotopic, for example, to the identity function on Rn. Okay, so now let's look at f composed with g. Observe that that's going to go from the singleton a to the singleton a. And in fact, f composed with g isn't just homotopic to the identity function, it's exactly equal to the identity function. But if it's equal to it, well, then it is homotopic to it since, well, I think that's pretty clear. Okay, nice. But now those two conditions being satisfied are exactly what we need given our definition over here for Rn to be contractible. Okay, so now let's look at another result. Okay, so for our next result, we'll show that if x is really any topological space and y is contractible, then for any two continuous functions from x to y, f is homotopic to g. Okay, so how could we do this? Well, let's suppose that f and g go from x to y are continuous. And then we've got to use the fact that y is contractible. And so we'll do that to bring into existence two functions h and k based on this definition of contractibility, which is homotopy equivalent to a single point. And so let's note that we have these two functions. So we'll say h goes from y to our single point, and we'll call that single point little y. We'll just take a 1-point subspace of capital Y, if you will. Okay, so we've got that, and then we've got k, which goes from our singleton y to our whole set y. And again, where y is just some fixed point within y. It doesn't matter which one. Okay, and these things satisfy the following conditions. So we have k composed with h is homotopic to the identity function on y, and let's see, h composed with k is homotopic to the identity function on that singleton, which is really just the only continuous function on that singleton for what it's worth. And now let's observe the following. So let's observe that if we take k composed with h composed with f, and we evaluate that at x, where this x is arbitrary inside our topological space x, but this is going to give us k of h of f of x. Okay, great. But now let's observe that h goes from y to the singleton. That means it takes everything in y just to this little y. But, well, what does that mean? That means this whole thing is just our little y. In other words, this thing right here is k evaluated at y. But now let's also observe that if we do k composed with h composed with g of x, we'll get k of h of g of x, which for the same exact reason is going to be k of y. And again, that's because h takes everything from y to that singleton. So that tells us that as functions, we have k composed with h composed with f is equal to k composed with h composed with g. As functions, we have k composed with h composed with f is equal to k composed with h composed with g. Okay, nice. But now let's put parentheses maybe here and here and use the homotopy equivalence. Notice k composed with h is homotopy equivalent to the identity on y. So that means this whole thing right here is homotopy equivalent to the identity on y composed with f, which is equal to f, just based on the fact that that's the identity function. That's what the identity function does. And then over here, we've got the same thing going on. We've got this is homotopy equivalent to the identity on y composed with g. But that's equal to g, again, based on what the identity function does. But now kind of deleting everything in the middle, you'll see that f is homotopy equivalent to g as needed. Okay, so now let's do an example or two. So now let's show that R2 minus the origin, so this is sometimes called the punctured plane, is homotopy equivalent to the circle S1. Recall that S1 is just all points in R2, so that x squared plus y squared is equal to 1. So I've drawn a picture here. Notice that S1 lives in R2 minus this singleton, so we can kind of put it here, and this yellow point would be the origin. We're thinking of that as being removed. Okay, so to show that these two things are homotopy equivalent, we need two functions so that when we compose them, we get things that are homotopic to the respective identities. So let's first consider the natural inclusion of S1 into R2 minus this point with which is the origin. So in other words, the punctured plane. And what do I mean by the natural inclusion? Well, you have a natural inclusion whenever you have a subset of a set. It's essentially just the identity function restricted to that subset. Okay, so that means that iota of xy is just equal to xy. And since 0, 0 doesn't satisfy the defining equation of S1, this most definitely goes to the right place. Okay, nice. And now let's also define a function going the other way. And so let's define a function f, and it's going to go from R2 minus the origin to S1 via the following idea, which we'll write down as a formula. So what it does is it goes out here to, maybe this is an arbitrary point in R2. And what you do is you connect this point with the origin. The origin's missing, but you can kind of think of it as being there. And then notice that that's going to intersect our circle exactly once, and that's how we're going to define this function. So if this out here is our point xy, then this intersection point right here would be our point f of x comma y. And then, well, what happens if you're inside the circle? Well, no worries, you do the same thing. So there we complete this line, and that's going to intersect the circle exactly one time, and that's going to be right here. You might say, well, these are going to intersect the circle actually twice because this is going to keep going out this way and this is going to keep going out this way. Well, I think we can fix that by changing my language a little bit. And instead of having these be the lines, let's say they're the rays starting at the origin going through the necessary point. And then it's only going to cross with the circle once. Okay, there we've got that. So let's see, if this right here is our other point x, y, then this right here on the circle will be f of x comma y. So now how do you do this? Well, in fact, if you've taken linear algebra, this should look kind of familiar. What we're doing is we're taking a vector and we're scaling it until it's a unit vector. So there's a straightforward formula for that, and it would be this. So this is going to be f evaluated at xy will go to the ordered pair x over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared. So you've got something like that. And now we need to look at the composition in both directions. So let's observe that if we do f composed with the inclusion, that's going to go from S1 to S1. And not only is that like homotopy equivalent to the identity, it's actually equal to the identity. So I think that's pretty clear. Notice that f composed with this inclusion is the identity function on S1. And that's because, well, if you stick something from the circle into this type of formula, your denominators are simply equal to 0. Okay, great. And then next up, we need to show that we have a homotopy equivalence between, let's see, iota composed with f and the identity on R2 minus the origin. So let's see how that might go. Essentially, we're going to use the same kind of trick that we used before. So let's take f, and so where does it have to go? So it's going to go from R2 minus the origin crossed with the unit interval, and it needs to go into R2 minus the origin. And what it'll do is the following. So f of x comma t is going to be 1 minus t times f of x plus t times the identity on R2 minus the origin. And you might say, well, I'm supposed to have f of x composed with the identity here, or I should have said, I should have here the inclusion composed with f of x, but that's actually not super necessary because observe that if we write this inclusion composed with f, that's just equal to f, just based on how everything works. F scales everything down to being on the unit circle, but then this inclusion is the identity on the unit circle already. Okay, great. But now if you wanted to write that out a little bit more thoroughly, it would be something like this. Okay, so in the numerator here we have t times the square root of x squared plus y squared, and then plus 1 minus t, and that's all over the square root of x squared plus y squared. And then that's multiplied into, well, our point x, y. Now you can plug in maybe t equals 0 and t equals 1 here, and you'll see that you go from our composition or from our function f to the identity as necessary, or you can really see it here just as easily. Either way we do it, we will see that iota composed with f is homotopy equivalent to the identity function on R2 minus the origin as needed. Okay, so there we have it. The punctured plane is homotopic to the circle. Now I'm going to leave you with some exercises. So here are some exercises. So the first is in the subspace topology of R. So the 0 circle, which is really just the 2 points, -1 and 1, is not homotopic to the singleton 0. But the singleton 0 is homotopic to R because we know that R is contractible. And then, well, also let's show that the one circle, which lives in R2 with the subspace topology, is not homotopic to the 0 circle. Okay, so next up, let's show that in the indiscrete topology, these two things actually are homotopy equivalent. And then finally, let's show this homework exercise down here. In other words, if X is homeomorphic to Y, then X is homotopic to Y. But then give an example where the converse fails. There's maybe an example where the converse fails on the board right now. Okay, and that's a good place to stop.